Okay, so we've got two more examples to finish this section off, and they're both of the form where you're given a function and you're asked to compute its derivative. Now, in the first example, this consists of two functions, both of which are compositions, and they have the property that the outside function is the natural exponential function. And I want to make sure to go through two examples of that form because for some reason a lot of people find these tricky. So I want to let's make sure we demystify these and go through them carefully. So for the first one, we're going to find the derivative of the function y equals e to the 6x. Let's identify exactly what the inside function is and what the outside function is. So I'm going to just space this out a little bit more so I can add to it. So we've got y equals e to the 6x. All I've done is just copy the function down. I haven't done any calculus yet. I haven't taken a derivative, and that's okay because I want to really take a moment to draw a bubble around that inside function. It's not just e to the x, right? It's e to the something, where that something happens to be the inside function 6x. So it's e to the power of the inside function, which is 6x. And say that out loud a couple times if you're not sure what to do, and that will lead you to the next step, because now we can follow the same process. If I want to calculate y prime, find the derivative, just start by saying, okay, what would I do if it were just e to the x? Well, the derivative of e to the x is itself, right? That's one of the functions that when you take its derivative, the function is unchanged. So when we go to differentiate the outside function, we're going to get when we go to the point where we differentiate the outside function but leave the inside function alone, I should say it like that, then we're going to get exactly what we see here. So we're going to get e to the power of 6x. So that is the portion of the chain rule that consists of differentiating the outside function but leaving the inside function alone. But remember, of course, now we have to multiply by the derivative of the inside function, and that's what we get. So that is a chain rule application when your outside function is just e to the x. Okay, well, now let's finish it off. So the derivative of 6 times x, well, if you do the power rule on that, you're going to get just the number 6. So in the end, you're going to end up having 6 e to the 6x. Okay, and that's how we can tackle that one. So it doesn't really make it any harder if your outside function is an exponential function. You just handle it exactly how you would treat any other chain rule problem. But the key is taking the time to clearly identify the inside function. And for people that struggle with the chain rule, make sure you're actually humoring me and doing this. Draw the bubble around the inside function. Make that your first step. Right? You'll find it really helpful. Okay, so for the second one, well, we've got another function kind of the same form. We've got f of x is given by e to the power of sine of x. So this is no different than the previous example, really, in principle anyway. The inside function is different. It's e to the power of sine of x now, instead of just e to the power of 6x. Or if you just look at the outside function, that would be e to the x, but what this function f of x is defined as is e to the sine of x. Okay, so again, ask yourself the question, what would you do if it were just e to the x? If you were differentiating this and it was just e to the x, well, you would just write down a derivative of e to the x, because e to the x is its own derivative. But here we have e to the sine of x, so we're going to start by just writing e to the sine of x. So that's the portion of the chain rule, again, where we differentiate the outside function but leave the inside function alone. But now we're going to multiply by the derivative of the inside function. All right, so that's the chain rule application. But now we can finish off the rest of the problem, because what's the derivative of sine of x? Well, that's going to be cosine of x. So really, what you get in the end is cosine of x times e to the power of sine of x. And that's the derivative of f of x. That's going to be your f prime of x now. All right, so that's what you do if your outside function is the natural exponential one, e to the x, then this is how you can handle it. One last example that we'll finish this section off with is a case where we have a composition of more than just two functions. Like if you look at this, you've got sine of cosine of tan of x. So on the innermost function, you have 3 layers, really. At the inside layer, you have tan of x. Then the next layer out, you have cosine of tan of x. And if you zoom out one last layer, your outermost layer is sine of everything else, sine of cosine of tan of x. So how do you approach situations like this? Does the chain rule work if you have a composition of more than two functions? And actually the answer is yes, you just have to apply it more than once. So I'm going to follow the pattern for beginning this. I'm just going to start by writing out the function a little bit more spaced out so we can look at its pieces. So I've got sine of cos of tan of x. Okay, so this is probably what you're going to want to do here. Identify what the outside function is. So like peel off the outermost layer, like I did here, right? So sine is the outermost function, and then just let absolutely everything else be your inside function. That's the way to start this. Okay, and then how are we going to proceed with our first step? Well, now we can just apply the chain rule, where sine of x is our outside function, and cosine of tan of x is our inside function. So when we start this, we're going to go f prime of x. So we're just going to differentiate the outside function. What would you do if it was sine of x? If it was sine of x, the derivative would be cosine of x, right? So we're going to start by just writing cosine of the inside function, cosine of tan of x, right? So we still have the inside function blurred out. The idea is if you were to relax your eyes, relax your vision so it got blurry inside and this green bubble just turned into an x, you would see f of x is sine of x and f prime of x is cosine of x. So that's how you should think about that first step. But that's just the derivative of the outside function. Now we need to multiply by the derivative of the inside function. All right, so that's the first step. But what you notice now is this is also a composition of two functions, right? This inside function, cosine of tan of x, when we go to differentiate it with this prime symbol, we're going to find out that this is also a composition of two functions. So we're going to have to use the chain rule again. So let's work that out at the bottom of the page. Like we can finish this off right below, but then maybe I'll have some space down here where we can work this out in detail. So let's work out the derivative of cos of tan of x. And that in itself is another chain rule application. Okay, so we have an inside function here, tan of x. So that's your inside function. Let's take the derivative now using the chain rule. So look at the outside function first. It's cosine of x. Or the outside function is cosine, I should say. Well, what's the derivative of cosine of x? If this were cosine of x, we would say that the derivative is negative sine of x. So we're going to start by saying negative sine, but then of course we're going to put in the inside function here, tan of x, and then we're going to multiply by the derivative of the inside function. So this is a chain rule application to find the derivative of the inside function. So this is now what we get. But now now we have another inside function, right? Our inside function is tan of x, so we have to take the derivative of that. Well, at least now this is gotten down small enough so it's no longer a composition, so we don't have to use the chain rule again. And it's handy if you remember, don't forget the derivative of tan of x is secant squared of x. So we mentioned that in section 3.3. So we'll get negative sine, finally, of tan of x times secant squared of x. So that is the complete expression that gives you the derivative of cosine of tan of x. So all of this is going to get subbed in for this, and that's how we can finish the problem. So finally we can say, okay, f prime of x is going to be cosine of tan of x, and we're going to multiply that by negative sine of tan of x times secant squared. And maybe we could write this in a little bit nicer of a form. It's kind of weird having that negative in there. Typically you would take the negative out and pull it out in front to write, and then we wouldn't need these brackets here. So that would be the best way to write it. So let's just take one more step to write this as negative cos of cos of tan of x times sine of tan of x times secant squared. Okay, and that is your f prime of x. So if there were a composition of 4 functions, or 5 functions, or 6 functions, you could still use the chain rule to take the derivative. You just have to peel one layer off at a time using the chain rule each time. So for example, in the first chain rule application, you can think of this as peeling off the sine layer, because it's the layer of the outside function, right? Because here we had to differentiate all 3. But then when we did the first chain rule application, the only derivative left had 1 layer less. Now this is only composition of 2 functions. So then when we worked that one out, we peeled off the cosine layer, and then the derivative only had the inside layer tan of x. And then finally, once we took the derivative of that, then we had everything gone. So just to be clear, everything below this black line, that's just extra work, extra details to show how we took the derivative of cosine of tan of x to get this expression here. Okay, so and to sum it up, it doesn't matter how many functions you compose, you can always use the chain rule to find the derivative, as long as you know how to differentiate all of each of the smaller pieces.